Let's look at something very similar to this last example. I'm going to change it up just a little bit. We're going to look at the series n equals 1 to infinity, 1 over the square root of n. So that's 1 over n to the 1/2. Again, this isn't a geometric series. It's not a telescoping series. So right now, we have no way of knowing if this converges or not. So let's do what we did on the last problem, the last example. We're just going to mimic what we did. We're going to first look at the partial sums and use a computer to help me add up a whole bunch of numbers, okay? So maybe I'll write it over here. So if I add up the first 5 terms, I'm going to get 3.2317. Add up the first 10, 5.0210. The first 50, 12.7524. Let me keep going. So add up 100 terms, 18.5896. First 500 terms, 43.2834. And we want to look at the partial sums again and see if they converge or diverge. So what do you think? Look at these numbers. Does it look like those numbers converge or diverge? Diverge, right? As I proceed on, the numbers start to continually get larger. It's not like the last one where the numbers stay pretty close together. Here, there's a big jump between the numbers. So we're going to start by saying what our intuition is for this problem. And again, our intuition says it looks like our partial sums, S sub n, diverges, which then tells me it looks like our series, 1 over the square root of n, diverges. So that's our initial kind of gut feeling that we've got going on, is I think that this series diverges. Okay? So we're going to repeat what we did on the last problem. I'm going to turn this into a function. All you've got to do is replace n by x. So our function is going to be 1 over the square root of x. And then we graph that. And again, you're only interested in positive values of x. Here, actually, this is the entire graph I'm going to draw right now. 1, 2, 1 over the square root of 2, 3, 1 over the square root of 3, and so forth. It's not quite as steep as the last one. Okay. And now we're going to calculate, we used a Riemann sum just like we did last time. But now I'm going to take and compute a left-hand Riemann sum. So I'm going to use the points on the left-hand side. Okay. That was not so great. And I'm interested in this area. So we're doing a left-hand Riemann sum. And just like in the last example, if I add up the area of these rectangles, so the first one, I'm going to get 1. They all have width 1 again. 1 over the square root of 2, 1 over the square root of 3, so forth. Again, this gives you my series. So this is my area of the rectangles. But these area of these rectangles are now, they go above my function, right? These rectangles. So now they have more area than the area underneath my curve. So what's going to happen is that the integral on the area underneath my curve is going to be a lower bound for my area of my rectangles. Okay? So the area of the rectangles is greater than the area under the curve.
So are you choosing whether to do left hand or right hand
Yes.
based on the graph?
Based on, it's really based on our initial decision if it converges or diverges.
Okay.
Our initial feeling, yeah.
So left hand if it diverges.
Well, you wanted to have a upper bound on the area of the rectangles.
Okay.
That's why you made the rectangles go underneath the curve.
Okay.
And then here, because I think it diverges, I want to have a lower bound. And so that's why the area under the curve is less. Yeah. Greater than the area under the curve. Y equals 1 over the square root of x for x greater than or equal to 1. So the statement is saying I now have a lower bound for my area of my rectangles, and that's the area underneath the curve. So let's compute the area underneath the curve. So the area from 1 to infinity of my function 1 over the square root of x, let's compute that. Well, first step, like always with improper integrals, we put in a limit, right? Limit as t goes to infinity, 1 to t. What's the integral of 1 over the square root of x?
Two square roots of x.
1 over 2? Because that's x to the negative first. Yeah, negative 1/2. Will be the square root of x. Oh, it should be 2, right? Yeah, square root of x divided by 1/2, so it'll be 2. From 1 to t. Yeah. So let's plug in our 2 square roots of t minus 2. What happens as t goes to infinity? What's that limit going to be? Infinity. Okay? Infinity. So what we just said is the lower bound for my area of my rectangles goes to infinity. Well then, that area of my rectangles can't converge. The series can't converge because this lower bound goes to infinity, so this bigger thing also has to go to infinity as well. Okay? So all of this is telling me that my integral, we just noticed that the integral of our function, it diverged, which now tells me that my series diverges as well. Okay. Any questions about any of that? What we're doing? So, mm-hmm.
So on that one, why, you didn't have to add something to the
Be-
beginning because
yeah.
there wasn't a rectangle out front, right?
Yes,
Okay.
there wasn't a rectangle out front because I did, I'm doing left-hand ream on some, so I'm only looking from one on,
Okay.
exactly.